I guess. So, I understand in week 8 you are doing the second test, right?
Yes.
Is it Thursday, same time?
Yeah.
Okay. Yeah, cool. So, basically, that's on Flexure, right? Has he mentioned anything about this test in terms of topics or whatever?
Yeah, week 4 and 5, yeah.
Okay. So, from Ench 1300, right, you might remember that, just checking this works, this is my first one doing something like this, right? We've got a simply supported beam, right? Two things, right? Shear force and bending moment, okay? Do you remember from 1300, these are the two things you calculate first?
The diagrams, right?
Yeah, the diagrams, yeah. Okay. Do you guys know what this looks like? Can you describe what these...
So SF will be linear and then BM will be quadratic.
Can I be annoying and like people will come up and, and draw?
Okay.
Okay, you do these two.
These two? Okay.
Right. Exactly, yeah.
And then BMD.
Yeah, exactly. That's a fish. Yeah, that's one.
Yeah. So, point load, so...
Yep, exactly. And then you can do that too.
This one is fuck. Forgot this shit.
Hi, come in.
What's that shit? So I'll increase and decrease.
Yep. Perfect. Alright, thank you. Okay. Yeah. Okay. So basically, from Ench 1300, you know that like in that course they told you to develop shear force and bending moment diagrams, right? And for Flexure, you're really only concerned. Sorry, not for Flexure, but like for the week 4 and 5 content, like you're really only concerned with bending moment, right?
Yeah.
And then that's, so for example, that would be the peak bending moment that you're comparing, right? So you're doing m star less than or equal to phi ms, and you also have to check it against the member strength, phi mb, right? So the thing is, like if you think about this, right, these are the external loads, right? What's happening on this beam is that, so that's the beam, there's transverse loads, right? So transverse loads just means forces that are coming at it perpendicular to its long direction, right? And these transverse loads, they induce two things in the beam, right? They induce shear force and they induce bending moment. So really, like two things are happening on this beam at once, but in week 4 and 5, you're only looking at one of the two things that's happening, right? Now, what I'm trying to get with this, right, is basically, when does shear, basically, firstly I'll show you what I mean by like peak shear force and stuff, right? So this is like the week 7 content.
Yeah.
And it's relevant because I suspect one thing that Brian can do to mix it up is ask you about the interaction between shear force and bending, which you've seen maybe briefly in like Farhan's notes from his assignment like last year, right? So in that like week 5 yap that Farhan did, you might have seen these values, what do you call it, symbols before, right? So V just stands for the shear, and the shear, right, is basically the highest at your supports, right? So that's the max shear, and then this whole thing is your max shear as well, okay? So what I'm trying to get at is, we don't know how to calculate this yet, right? That's the shear capacity. You may or may not have watched the videos to calculate your bending capacity, but the question is, again, just focusing on the left-hand side here, when do you have values for M star and V star, which start to govern, right? So both things are happening at once on your beam, right? And if you look at AS 4100, right, the steel standards, right? Under the topic of flexure, right, just like members in flexure, you see both bending and shear, okay? So flexure is just the fact that your beam is taking transverse forces, right? That's what flexure in general means. And then you find the bending capacity and stuff. But directly under it is your shear capacity, because shear is heavily tied in with the concept of bending as well, okay? So, yeah, anyway, what I'm trying to get at is, for the case of a simple beam, and where you have uniform loads and or a point load, right, two very common scenarios, you have the max bending moment in the middle for both of these, and you also have your max shear at the edges, right? So, what I want you to think about, let me get a different color for these pens, right? What I want you to think about is what happens, okay, forget the uniform load for a second. What happens to that shear force and bending moment diagram if we shift P to the side, okay? Draw this in your head. Like, I'm not gonna make you come up and draw this, okay? Just draw this in your head. Okay, so shear force, instead of being even, ends up doing this. Okay, so the left block and the right block, in terms of its area, has to be equal. This is in order for the bending moment to end up being 0 in the end, right? So you go up to some max and you drop back down to 0. So area 1 has to equal area 2, right? But what has happened to our shear force? Which one's bigger, the block on the left or the right in terms of its max height?
Left.
The one on the left, right? And so you can see what I'm trying to get at, right? The bending moment from the original loading case, right? Let's just say it's here. The original loading case resulted actually in a higher max moment, okay? So the worst case scenario is for bending is if your point load is positioned right in the middle of your beam. Like you can imagine if you had like a stick, right? And then you put a transverse force like right down the middle, it's going to break the most easiest if you put the force on the middle, right? But you can see it actually dropped. It actually dropped in terms of its moment when we've shifted P to the side. But the shear force has increased, right? So you can imagine if we do a more extreme loading scenario, right, for this point load. I'm just going to exaggerate it. You see what's happened? Yeah. Now we have an extremely high shear force, right? And a rather low bending moment. Yeah? Okay, so what's a physical example of shear failure? Okay, so if I had a piece of paper, we're looking at a piece of paper sideways, right? And I have your blades of your scissors, right? In and out of the page. That's the force due to one side of the scissor, and that's the force due to the other side of the scissor, right? So what the shear force diagram of this would look like, let's just say support on both sides, is like that, right? So when you have 2 point loads that are very close to each other, including reactions, right, from your support, you get a very, very high shear, okay? And that induces shear failure, okay? Okay, so without much more about that, I want to talk about, looking over there, I want to talk about flexural shear, okay? Now I know you care about flexure more, so I'm going to focus on number 3 of my notes more, which is your shear and bending capacity and its interaction between itself, okay? So if I just scroll down to that, there's 2 methods, right, which you care about. Number 1 is the proportioning method, and number 2 is the interaction method, okay? Now, Brian, in previous assignments and stuff, let me check I'm on the right document, yeah, has cared more about interaction method, right? Like I've never, and also Hamid, I've actually never seen this method utilized, right? But it's essentially based on the assumption that the bending moment can be restricted only by the flange. Okay, so what I mean, so what you'll learn in this topic, once we cover it properly, maybe today, maybe another time, is that this is the web, and then in the blue is the flange, right? We say that the web takes the shear, okay? And you'll see that this is reflected in the formulas. Majority of the shear resistance comes from the web. And then, as we know from flexure, the flanges take most of the bending moment. Right? So this is because your moment of inertia, right, your I value, it has like parallel axis theorem, right? So the further away your bit of metal is from the neutral axis, from the bending axis, the more it contributes to stiffness, right? Flexural stiffness, which is Ix, let's say. Okay, so the flanges take the bending, and the web takes the shear. And so what this is talking about is if your bending moment is able to, if your bending moment from just the flanges without any contribution from the web is able to take on the max bending moment, then happy days basically. And yeah. That's what the proportioning method is, okay? But the interaction method is a little bit different, okay? So if m star is less than or equal to 0.5 ms, okay? So I'll tell you what that means in a second. Then so this means shear. So V stands for shear. Vm is shear, so shear capacity. And then the comma means shear plus bending together, right? So the capacity of shear capacity when it's shear and bending happening with each other is just the full shear capacity, okay? But the shear capacity of shear and bending together has to be reduced by some amount, right? So this is like some calculation to give you how much it gets reduced by in this second scenario. Okay, so what do these scenarios mean? So in the first scenario, right, if you imagine, how do I say this? If you imagine this is your HP bar, right? You're playing Clash of Clans or whatever, and then your entire HP is 5 ms, okay, that's your capacity. And then m star is the damage, right? So the idea is if this damage bar has exceeded 75%, if it's less than 75%, then we do case 1, okay? That's case 1. And case 2 is if the damage is greater than that. Okay, and then we have to reduce it. Does that make sense? Okay, so, yeah, this is the reduction factor, and you might have seen some kind of table before. What I'm going to do is I'm going to open up a document. So, Steelfixer's handbook, where is that shit? I don't think this thing's bookmarked, which is annoying. Interaction. Bending interaction. Okay. Okay, so this graph, right, it's not directly in the standards, but you see it a lot in terms of like diagrams which represent what's going on. Okay, so the first thing that's going on is this axis represents the amount of damage to HP in terms of shear. Okay. So this is the damage to HP of your shear. Yep.
He drew that in the lecture as well. But
oh yeah. I think Brian actually makes a big deal out of this graph, not gonna lie.
But he drew it with the moment ratio being on the y-axis.
Oh, okay. Okay.
Same thing anyways, right?
I think if you rearrange, it's the same thing. But I prefer looking at it this way. And the reason, I'll show you the formula again. Okay. So y-axis is this one. And x-axis is this one, right? So, yeah, basically, if the damage is too high on both of them, even though they haven't individually failed, right? So say you're at like 90% damage and 90% damage for shear and for bending, you're in the unsafe region. That's what it's trying to say. Do you know what I'm saying?
Yeah.
Yeah. So this line, right? This line here is what that formula that you saw before was, okay? So if I go back to that formula, right? Okay, you have to do a little bit of like mental gymnastics, right? Because, I forgot the exact way that you're supposed to rearrange this formula, but basically that line there, when you're graphing it against V star over 5VV and M star over phi MS, right? At phi MS is equal to 0.75, so this is 75% damage threshold, then you have to basically start to reduce this thing, okay? Yeah, like graphically, there's some way to represent it. I forgot, because basically you have to like you have to fuck around with this equation and this equation until it looks like this is the y-axis and this is the x-axis. Yeah, come no, yeah, go fuck off.
Come in confidently.
Why isn't he coming in? Let me get it. Okay, whatever. Okay, but does that make sense? Okay, so that's bending and shear interaction. And that's probably the most relevant bit of information for your exam. Because even if he doesn't directly test how to calculate shear, so remember VV is the calculated shear capacity, right? Which is technically supposed to be covered in week 7. He might just give you this as a value, I suspect. He might just say, pretend this is 100 kilonewtons. And he might see if you know how, like whether it's going to fail or not with the other information that's provided, right? Do you know what I'm saying?
So what is VV again?
Oh, okay. Do you want me to cover that?
Sure.
That's the shear capacity of your beam. So you know how you've calculated the bending capacity of the beam? Yeah. That's MS and MB?
Yeah.
VV is the equivalent, but how strong it is in shear. Okay, so if your phi MS, right, so your HP is like 100 kilonewton meters, right, you would have done a different calculation to find phi VV, and let's say that's also 100 kilonewtons, right, so instead of kilonewton meters, right, in shear it's kilonewtons. So that's the maximum amount of shear force it can take.
Oh, right, okay.
Yep. Did you have a question?
What's the square graph?
Sorry?
It's like the square graph thing.
Okay, so if I go back to the Steelfixer's handbook, right? One second. So it's a square because you can't go over the damage threshold of 1, right? So you can't go over 1 because then your beam would already fail. So you know that this portion out here is already unsafe, right? Right. And then the same thing goes for over here. Okay, I'm just not going to write it. But what the formula is trying to say is it's trying to draw this line.
That's the formula you had before.
Yes. Well, it's not shown in the same way. It's really annoying. I think Farhan did this last year where he rearranged to find the line graphed out. Okay, I'll try to re-explain it because I feel like I didn't explain it very well. But the idea is this is a failure envelope, right? So everything inside these 3 lines, so this one and this one, so everything inside these 3 lines is safe and everything outside is unsafe. That's what it's trying to show, what it's trying to tell you, okay? But in terms of how to graph how to actually graph this line, I'll tell you what you have to do. I'm not going to be able to do it like on the fly, but you go V star is less than 5VVM, and then and then you basically replace this with this whole thing. Sorry, with this whole thing. Okay, so that whole thing becomes VV bracket 2.2 minus 1.6 m star, sorry, over phi ms. Okay, and on the left hand side, if you rearrange it, right, such that you bring these two out the front. I forgot the exact way you do it, like, yeah, but basically it will say da-di-da. So it's like mx plus b basically, right? Mx plus b is your straight line equation, right? So the slope will be negative, so there'll be some negative slope for m. Your x value is this, right? And then plus b, right? And then that b value is however high this line has to be to intercept the y-axis. You know what I'm saying? Mm-hmm. Like, I forgot these exact values, and if you go on Symbol Lab and you tell it to rearrange for this instead, it'll give you the correct values, right? There's some way to graph it, basically.
So would they ask for that exam maybe?
Like, low key, I feel like in the assignment, Brian's done that before.
Finally, yeah, probably, yeah.
He asks a lot of questions which are relevant if you're maybe like a researcher, but not really if you're like practically doing stuff as a student learning to be like a structural engineer. So this is like something that doesn't really matter, like trying to rearrange equations like this by hand. But I've seen it be assessed before, which is kind of silly, but you know, whatever. Sorry? Oh yeah. No, but anyway.
But I mean, this is not something I have to be concerned about for next week, right?
No, because you don't have to rearrange this equation. I'm just showing you what it looks like graphically. All you have to do is check that. All you have to do, if he gives you something like this in your exam, so what I'm trying to tell you is like, he can't assess you, I think, on how to calculate shear in this upcoming exam. He can't, but he can give you a value for it. So it's like, he already tells you what the HP is, right? And then it's like, okay, do you know how this formula works? And whether it's going to break or not, right? That's what I'm trying to say. Because if he's covered it in the lectures, right, you said?
But this is covered just yesterday.
That's what I'm saying. Like, it's accessible material because it's talked about it now.
Oh, yeah.
Yeah.
No, but he meant, yeah, for the exam, yeah, sure. But he mentioned for the test next week.
It's not.
It's only on, he said revise on week 4 and week 5 content.
Okay.
Okay.
That's fair enough then.
Yeah.
Okay.
I mean, yeah, it's good.
Keep this in your back pocket.
Yeah,
that's what I'm saying.
Like throwing curveballs all the time.
Yeah. Like, you never
yeah.
know. Like, I don't know what the exam looks like, so I'm just trying to prepare you guys the best as possible, right? And you'd rather be over-prepared than under-prepared, right?
Mm-hmm.
Okay, so I don't know if I should talk about this week or next week. I'm thinking about it. To be honest, I'd rather keep it brief today and then go through it properly next week when you guys care about it more.
Yeah.
What I might do is I might just run through very, very broad strokes concepts for beams in general that relate to shear, and it might be related to flexure stuff, okay? So the first thing I did in my demonstration earlier was tell you when you have high shear force, right? Compared to high bending moment, right? So bending moment's the highest, right? This is what I was trying to illustrate on the board. Bending moment's the highest when it's like applied in the middle, right? But shear force is the highest when you apply it as a point load next to a support, right? So we know that this is called the web of a I-beam, right? And here we've got an unstiffened web. So, yeah, see ya. Okay. So a web panel is how you decorate the inside of the web. So this region here. And like, why would you want to do this, right? There's a few reasons. The first one is you want to resist bearing. Okay. So you know how I was talking about the point load from earlier? So you imagine a point load on this beam that's really, really high, for example. What happens is that this beam actually wants to buckle, right? Do you know what I'm saying? If it's really slender, like the web. And so what you might want to do in that case is add stiffeners, right? So this is just called a stiffened web.
That's just a single plate, right?
Plate on both sides.
On both sides.
Yeah. So that basically increases the buckling capacity in that localized region where there's a point load, right? And you might want to do the same thing on the reactions, depending on what the reactions are, okay? So that's stiffened webs. And there's different terms we use for the spacing and the depth and stuff like that. You might also see longitudinal shear stiffeners, and it's a similar idea where you're basically restricting. So if I take a cross section here, right, it looks like this, and then you've got a longitudinal stiffener. Here, if you think of the web like a column, you've basically restrained it in the middle from buckling. So instead of a localized kind of effect, this entire region that has this longitudinal stiffener has a restraint in the middle, right? So you know how when we're talking about columns and compression, we were talking about effective length?
Yeah.
We've halved the effective length by adding a longitudinal stiffener. So that makes sense? Yeah. Okay, and one more type, which I haven't included here, is sometimes I've seen adding additional webs. So you might want to weld a plate. You might want to weld additional plates on. Okay, like this. So, for example, what you see here, there's 3 webs now. Okay. Do you guys want to guess why you might want to do this? You don't want to guess why? Okay, basically, you have to understand how shear forces flow, right? So, if this is a I-beam, right?
Because one of the flanges is in tension and the other one's in compression.
No, not really. Like, you're right.
Yeah.
That does happen, but that's more axial forces, not really shear. We're talking about vertical shear.
Okay.
So how shear forces want to flow is it goes vertically through your I-beam from outside in, basically, right? And the majority of your shear force will be taken by your web, okay? Just trust me for now, right? It makes no sense until you see the calculations. But if you have, I'm running out of space. If you have 3 webs, actually, let's just make this simpler. If you have 2 webs, right? There's actually more paths for your loads to flow, right? So your shear stress in each of the webs gets halved, right? In this case, does that make sense? And so if you add an extra web, you basically halved the amount of shear stress in the web itself. So you double its capacity. So you add 2 extra webs, you've increased the shear capacity significantly. And this is important because when I was designing something as like a structural engineer grad, right? Okay, I'll tell you the exact scenario that happened, right? Well, I'll try to simplify it. So we had a beam, okay, and we had a really, really high point load here, okay? And this is the first time I've ever run into this situation because a lot of the time you have a column, say like above and below a floor, okay? So that's a floor in purple, and then above you have a column, and below you have a column. So what happens is this is a direct transfer of load. So if you imagine it like the stacked toddlers example that I was talking about before, this is like there's no offset of that load. The weight from the toddler on the top transfers to the toddler at the bottom. But what happens is if your column is offset, this now becomes a transfer system. Okay, where not only does your force have to travel vertically, but it has this kind of diagonal load path, right? So that'd be like if there was a a surfboard on these dudes, and this dude's stepped to the side or something. When you have a transfer system, right, your column above doesn't land directly on the column below, right? So this might be the column below, and this might be the column above carrying the weight. So imagine there's like 500 toddlers, right? Like above here. It has all these toddlers' weights, right? And then it has a transfer over here, okay? So this is actually a system where these toddlers at the top are treated like a point load, and then the support is that toddler at the bottom. Do you know what I'm saying? So this is called a transfer column system, right? And in these cases, the shear force was extraordinarily high there, right? And this is the only time I've ever seen shear force govern. Like I designed probably 100 to 200 beams last year, depending on whether you count like duplicates. And this is one time shear ever governed, okay? And my senior, who had been a structural engineer for 10 years, has only ever seen it govern 3 times in his whole career. So it's super, super rare. But yeah, we still have to calculate the capacity for shear, for the shear capacity of these steel beams, right? In the case that it does. Okay, so what happened in this, I might just like change this a little bit, right? What happened with this shear force diagram, right, was that this, like, basically the shear force here was failing the entire width, the entire length of the beam, that the shear was too high. And so if you think about what type of stiffener you want to introduce, right, you're not trying to prevent the buckling due to the bearing, right? You're trying to stop this thing from shearing, right, from cutting off, right? So this entire thing is being sheared. And so what you want to do is you actually want to add extra webs to the beam in this region. Okay? So that's this, right? You want to add extra webs like this. And this is the way that you would improve the shear capacity for this entire region, not just the localized region, against shear. Okay? Does that make sense? And you might even like overrun it a little bit. Okay. So yeah, there's bearing. I talked about bearing. Oh, sorry. I mentioned bearing briefly. We might talk about it more next time. I mentioned flexural shear, and then flexural tension just means bending failure. And that's the axial loads and stuff you're talking about with like the flange and tension and flange and compression. That's more for bending.
Okay, gotcha.
Yeah. Because I know what you're trying to say. Because you're saying that this top one might be in compression, this bottom flange might be in tension, or vice versa. Like you're right, but we're just talking about something else right now, which is shear. Yeah.
So like it does happen. It's just that it's not really that relevant in that case that you're talking about. Like it wouldn't govern. Or...
Okay. Think about it like this, right? I'm just gonna make up some stuff. Okay. Pretend you're doing a double degree in commerce and engineering, right?
Yeah.
And say for whatever reason you have a WHAM calculation for your commerce subjects and for your eng subjects.
Yeah.
Your WHAM that affects your commerce subjects, like that calculations, is only affected by your commerce subjects.
Yeah.
And then the WHAM that's affected by your eng subjects is only affected by your eng subjects, right?
Yeah.
So what you were talking about is, say for example, just the eng subjects.
Oh.
And then what I was talking about is just the commerce subjects.
Oh, okay.
Right. And then the thing I was talking about earlier today was the interaction between the shear and the bending.
Yeah.
That's the combined WHAM
of
all your double degree subjects together.
Yeah.
Okay?
So it's usually treated separately except when it interacts?
Yes.
Okay.
Pretty much. Yes.
Oh, okay. Gotcha.
You do both checks separately,
and
then there's a combined check.
Oh, okay.
Yeah. So what I was trying to tell you before was the combined check.
That was the square thing.
Yeah. The square thing was a combined check.
Okay.
But you basically haven't been taught one side of it.
Yeah.
Which you'll learn later, and therefore he can't test you on it.
Yeah.
Apparently, according to what he said. Okay, that's pretty much all I had to say. These other ones don't matter yet. Okay, we'll talk about it next time, alright? Alright. Do you guys have any more questions for the moment? It's pretending like she had questions to begin with.